So in this video, we're going to look at the concept of completing the square, kind of as a solution process for quadratic equations. The issue that we have had so far is the techniques that we've used to solve quadratic equations have all relied on certain things being true. They've all relied on the situation being kind of contrived so that the solution technique can be applied to the quadratic equation. So for example, we've looked at quadratic equations that are missing the linear term, and we saw that we could use the square root property to solve those. We saw quadratic equations that were missing the constant term, and we discovered that it was easy to factor and use the zero product property to solve those. We looked at a technique called grouping, and in the grouping technique we took the leading coefficient and multiplied it times the constant term, and then we looked at the factors of that product. So -6 in this case, -1 times 6, 1 times -6, 2 times -3, -2 times 3. And once we got all the nice factors, these are all nice factorizations, we looked at them and asked the question, do any of these factors add up to the coefficient on the linear term? And in this case, none of them do. And if none of them add up to the coefficient on the linear term, then using the grouping technique is not going to be easy. So in fact, this quadratic equation, although it looks simple, none of the techniques that we've used so far can be easily applied to solve that quadratic equation. And so what we want to do is develop a concept and a technique that allow us to solve quadratic equations in general. And the concept we're going to play off of is called completing the square. And here's the idea. The idea is that if you think of the variable x as representing some unknown length and having a constant a that represents another length, and this could be a negative. We could introduce the idea of negative length. We don't need to do that for our purposes to get at the kind of the concept or the gist of what's going on here. But if I look at this as being a length, this has length x, this has length a, then the total length across the top of this square would be x plus a. And I've constructed a square, so I know if this is length x here, I know that this length right here is also length x, and I know that this length right here is also length a. So I have a square that's x plus a units wide and x plus a units high, where a could be a signed number, and that would be all right. And the idea is, if you want to calculate the area of a square, what do? Well, if you know the length of a side, you just square that length. 5 squared, or 5 times 5, hey, this square has area 25. So if I want to know the area of this large square, what I can do is take the length of one of the sides, which is x plus a, and just square it. And to square a binomial, we know we need to multiply that binomial by itself, which is going to give us x times x is x squared, plus we get, by the distributive property, x times a gives us an ax, plus a times x gives us another ax, and then we would get a times a to give us an a squared. And what I want to recognize is that these four terms actually correspond to the four areas that this square has been broken into. So for example, right here I have a square that is an x by x squared. So its area would be x times x is x squared. And here I have a rectangle that's x high by a wide. So I would get the area of this rectangle by multiplying a height of x times a width of a. So I would ax. And here, this rectangle is identical to this one. It has a height of a and a width of x, so its area would be a times x. And this little square right here is going to be a wide by a high, so I would get the area by doing a times a, which is just a squared. And if I add up the areas, I get x squared, which corresponds here, plus ax plus another ax plus a squared. So squaring this binomial like this actually gave me the area of the 4 regions that my square has been broken into. And I can simplify this a little bit. I can say, hey, x squared plus ax happens twice, and those are like terms, so I get 2ax's plus an a squared if I simplify it. And what I want to recognize when I look at this area, this is an area calculation here, that the number that's being squared right here is half the coefficient on the linear, or x to the first term. In other words, if I took the number 2a and I divided it by 2, I would get a, and a is the number that's being squared. And we can use this idea to complete a square if we have missing information. So here's an example. Suppose I had x squared plus, let's say I had 6x plus, and I wanted to know what number to put here to finish off the area. So suppose I don't know what number to put right here in this position. I don't know what a squared is. In fact, I don't know what to put here or here either, but here's the idea. If all I'm missing is the a squared term, which is what I'm missing here, what I want to realize is that the middle coefficient, that x to the first power coefficient, has to be twice the size of a. In other words, 2a needs to equal 6. And if I do that, if I want to solve for a, then I just divide both sides by 2 and I get 3. So now I know that I had to multiply a 2 times 3 to get the 6. And the number that needs to go here, remember this is an a squared, so if a is 3, then here I would get a 3 squared, which is 9, and this would be a 3x plus 3x to get 6. 3x plus 3x is 6x, plus this number would need to be a 9 in order to complete the area of the square. So this is the concept of completing the square, the idea that the middle coefficient is always half the number that you need to square to get the area of this last little square in my larger square.